Yes. Okay, welcome back everyone. And our next today is with Dr. Binod Bhattarai. He's also from University of Aberdeen, but he'll be presenting his talk on a different area. So it's a kind of opposite now, more on the data science side, but also in context of healthcare. So Dr. Binod Bhattarai is a lecturer in machine learning and the head of the multimodal labs at the University of Aberdeen. He graduated with a degree in electrical engineering from India, and then after that he went on to do a master's in computer science at the University of Saarland in Germany. He then went on to do his PhD in France at Normandy University, and then he went to industry for a few years as data scientist at Telenor Group, which is based in Norway. He then went back to academia, where he did his 2 postdoctoral positions, first at Imperial College London, and then later at UCL. And then Binod joined the University of Aberdeen in 2022 as a lecturer and principal investigator. And he has research interests in machine learning, computer vision, natural language processing, and medical image analysis. And he's also the head of research at Foxsphere, which is a London-based IT company, focusing on computer vision AI sensors to aid in workplace security. He has multiple awards, such as namely the Google Cloud Research Innovator Award, which was awarded to him in 2022. And he was also recently the runner-up of the Arcade Challenge, which was hosted by the Medical Image Computing and Computer-Assisted Intervention 2023 conference in Canada, Vancouver. As mentioned, he has interest in medical image analysis, and this specific interest will form mostly the basis of his talk today, which is titled Federated Learning in Healthcare. So without further ado, I'll hand over to Dr. Bhattarai, and thank you very much for giving your time today to speak to us today. Thank you.
Thank you so much for a nice introduction, and good morning, everyone. Sorry, I could not be in person there. I'm in annual leave, but thanks for having me. So today I'm going to talk about some of my research in federated learning in healthcare. So my background is in computer science, that you know, I think you know from my introduction too, but I have great interest in healthcare. So I believe most of you have a background in healthcare. So, you know, I try to basically balance my talk in both healthcare and computer science, but the expertise in healthcare is limited. So yeah, I mean, I lead multimodal learning lab in University of Aberdeen and Naumi, Nepal. So Naumi, Nepal is a research lab institute based in Nepal, which actually I co-founded in 2018. So today I'm going to talk about federated learning, and my research team is also kind of federated. So we are in the different 2 parts of the world, and but then we exchange so although we don't be present physically, but then we work remotely and we exchange our experiences, and we update each other and share the experience without being physical presence. So this is a kind of federated team for a research team for me. And so our focus is in machine learning algorithm for processing information from both text and real text, image, and other sources of information, which can be heterogeneous in nature. And we develop algorithm to enable computer to understand, interpret, and reason. And our applications are in computer vision, medical image analysis, energy, and so on. And so we are generously funded by the Royal Academy of Engineering, Indomapper project, and some of the industry partners. So I will start with what is machine learning first. So machine learning in simple terms is, teaching computers to generate, to learn data and make decision. So you can see 2 diagrams here. So actually the diagram, this is actually on the left-hand side. It is generated by DALL-E. It's kind of ChatGPT. I think you must have heard about this thing. So these are also like AI. So underlining a principle behind them is AI algorithm, machine learning algorithm, trend, by large amount of data, and then they are able to make a decision or generate similar kind of data when we make queries. So this is a symbolic picture of machine learning here. So there is a machine like humanoid, and it is like perceiving information from different sources, and that is being processed and being interpreted, something like us. So we have different sensory organs. One of them is, like eyes, ears, skin, and, we perceive the information from the environment, and then we process it and interpret it and make decision. Something similar in machine learning too. So the data can be in a different form. So it can be in the form of time series, it can be form of image, or it can be in the form of text, and so on. And the idea here is to, we train a model with some training examples. So for example, you can see on the right-hand side. So this is the images. So these synthetic images. So I'll talk about this synthetic. I won't go into the deeper about why synthetic images, because there are certain limitations. We can't collect real data all the time. But then, so this is it looks like synthetic images, and it's the synthetic images, synthetic image of colon, human colon, and then the right-hand side is a depth map. Like depth map is like how far the linings of the colons are from the camera, the endoscope. And we train the model, so it can be encoder or decoder, we call it, and it can be, commonly known as deep learning. And we train them using such examples, like, the training examples. And once this model is trained, then this model should be able to, make correct predictions, or should be able to generalize on real data. So this is about, in general terms, what machine learning is about. So there are different types of machine learning. So one of them is called discriminative models, and another are generative models. So discriminative models are something like, that gives us the idea about the category. For example, you can see here this images. So this image is a colon image from endoscope camera. And this model, machine learning model, what is doing here is that, it is classifying the pixels of images into whether those pixels are healthy tissue, belongs to healthy tissue, or the disease or anomaly, right? So this is a kind of discriminative model, we called it. And generative model is, this generates new data similar to original data. Like, for example, this is the X-ray image, and this was the original report, clinical findings. And the below you can see is from Myra. So Myra is a generative model from Microsoft, released this year. So these are the two broad kind of machine learning. So ChatGPT and all this thing, you must have heard about them. So this belongs to generative model. So these are the broad two category of machine learning. And so for this kind of task, deep learning has been widely been used, for both modeling both the types of model, that is discriminative and generative model. So deep learning in healthcare. So deep learning, it's a very common buzzword now. And so then what is deep learning is about? So deep learning is a subset of machine learning, or also, like, in general, if you look into the broader term, so there is a big discipline called artificial intelligence, like it's physics, chemistry, or medicine. So then in this artificial intelligence, there is machine learning, and inside that is deep learning. So it's a kind of machine learning technique. So this is called deep learning because, it has different layers, deep layers, not just your shallow layers, but it goes through several layers and process the images or the information into different layers and before making the decision or prediction. So this kind of architectures or learning paradigm has shown a lot of promises, but the problem with this kind of, training this kind of algorithm is these are data voracious in nature. So, it needs a lot of data to train a model. So which is a major bottleneck in medical domain. So before diving into medical domain, I would like to show you some figure here, facts and figures about the data in computer vision. So this task was about face analysis, and I have kept one boundary as 2012 here because that year this famous deep learning architecture called AlexNet came into, was invented. And then, so we can see the shift in paradigm shift in collection in terms of collecting data before and after this year. So before this year, so there used to be the benchmark with few hundreds, few thousands, and collected in the controlled manner. But after this deep network, the data, the need of data, it started growing from few thousands to few hundred millions. Now, there are millions and billions of tokens or the text corpus are being used to train the model like ChatGPT. So although they are promising, then how are we going to deal with this, in terms of healthcare? Because in healthcare, we can't collect the data in that magnitude, right? And because of many reasons. So it can be costly, or it needs experts, it's time consuming. Also, the most important thing is the concern about the privacy, like the patient's information. That's just very sensitive information. So now, then, how do we deal with that? So there are two things, like, we need a lot of data, and there is not a, there is a big challenge to share the data across the different institutions. Unlike computer vision, we can get many images on the internet, but which we can't get for medical imaging. So that was the data set, the benchmark in computer vision. And let's come back to some medical use cases, okay? So this is a size of data sets in medical domain. So if you see here, so here are the data. These are like, the data set collected at 4 different centers in Europe. So in Norway, UK, France, and Spain. And that is used with, actually, this data set is for, the segmenting the polyps that I showed you before in the introduction slides. So if you see the magnitude of the data here, so it's very small, like few hundreds, even less than 100 images are there. So now, how are we going to train the model that requires a lot of data? And the thing is that, these are collected in certain research center or the medical, hospitals, and this data we can't easily ship across the border. Right. So because of privacy and GDPR and all these compliances. So in this situation, federated learning can be an option. So then what does this federated learning means? So federated learning means like there will be n number of clients, so the client and the server. So clients are basically your computing infrastructure in your institute, let's say in the IMS or other institute, right? So then you collect your data, then you train your model in-house. So this can be Institute 1, Institute 2, Institute 3, and so on, right? So now you train your own deep network locally. Then instead of sharing the data across from these clients to the server, so what you do is you share the parameters, not the data, raw data. So these models parameters are aggregated in a way, like, we compute the high statistics of these parameters, model parameters, and then we share them back to each of the clients. And then we keep on learning iteratively. So this actually would help us to learn the model without sharing the data, and also tackles the problem of scarcity of the data in a collaborative way. So then how does this federated learning compares with other methods that do exist, which are very common? So one of them is called standalone. So standalone is like you own your data, you have your network, and you train within your premises, right? With your data only. So this is standalone, and which is very common now in medical domain because of the aforementioned challenges, like we can't share the raw data across, from even within the UK, from one institute to another institute. I mean, it's difficult to ship the data. Right. And then another approach is, which is like there are n number of institutions, they basically curate the data, and this data can be basically brought together in a server, right, or create a data lake and combine them and train a model. So which also exists, but this technique would bring the challenges that I mentioned before, like privacy concerns again. And the federated learning, just I mentioned before, is a technique that helps us to train a model without sharing the raw data. So this is how it compares. Federated learning just shares the model parameters which are not interpretable, and also prevents us from these compliances or the privacy issue. So with this feature, the advantage, federated learning brings several advantages. So sharing, learning the model in a collaborative form tackles the problem of data scarcity, and also it also helps us to mitigate the collection and feature bias, because the patient data collected in a geographical region may belong from certain ethnic group, or and maybe there maybe not be a lot of diversity. So if we enable such, if we do learning with this federated infrastructure with the data collected in different geographical region, then the model that we develop may be not biased to a specific ethnic group, or certain age group, or so on. So these are better models and provides good performance, and definitely these provide the privacy, like model weights are cryptic and more secure because they are not, they don't disclose the information about the patients. And also the thing is that, with the clients, with the laser data, you don't need to have a very big, basically the server to host the data, right? You can basically share your resources, collectively train, and then also get advantage to each other. And so again, as I said, reduced compliance burden, and this can be scalable and more resistance to failure. Failure in the sense like, the data are also, if you are there in the n number of clients, then if one of them fails, it's not like if we just collect the data in a server, then if the server in a single server, then if server fails, then everything goes away, right? So basically, it also helps us to the resistance to failure. So this is the comparison here that we have made between this standalone federated via data lakes and federated learning and different attributes, for example, in terms of data collection bias, prediction, privacy, and data storage needs, cost effectiveness, and so and so. And the green means the positive aspects, and the red means red signal. So in these attributes, federated learning brings the advantage compared to the existing common techniques. So although it's a very useful tools and technique for the privacy and data scarcity problem, but then it comes with several technical challenges. So one of them is data heterogeneity. Like, for example, there are different ways. Data heterogeneity means like, for example, I'll take the reference of some of the clinical use case later in the slides. So the way the data is done, acquisition of data is done, that can differ from one medical institution to another institution, because there are certain cases where the skill set of the health professional also matters, the way you do acquire the data, right? And then distribution shift means like there can be prevalent of certain diseases in a region, but maybe not in another region. So this is called kind of distribution shift. Maybe some diseases are present, common in certain part, and not not common in the another part. So maybe there won't be the uniform distribution of this data. And the communication overhead is like, we have to push the model that we train locally to the server. So that also a problem, the technical challenge it brings. And security risk is still like, although we share the model parameters, so there are still like, there are some issues. There is still some possibility to uncover the certain level of patient information. But definitely it is more secure than sharing the raw data, but still there is some can be some issues and loopholes. So there is certain level of security risk is also there. So I'll start with some clinical use case. So one of them is that we are working on, doing the research in Aberdeen. So this is one of them is polyp detection. So polyp detection, these are the images captured by the endoscope, the camera, and the task is to detect these polyps. The early detection of these polyps is very important. So the study has shown that if we detect this, manage to do the early detection of polyps, then their survival rate can be increased, and also the study has shown that endoscopists may miss up to 30% of detectable polyps. So it's very much important to detect them, so to prevent to increase the survival rate. So one challenge that I mentioned before is that if you want to go for federated learning, and then see these are the data. So these are the data collected at different centers like CAVAS here, Indo-UDA. So for example, this is Norway, Indo-UDA in Oxford and France and Spain. So I mean, these are the data collected for the same task, like detecting the polyps or the segmenting the polyp. But because of this lighting conditions and also, like as I said, the level of expertise, of endoscopist, so the data that you collect can vary. So simply applying this federated learning and aggregating the parameters may not help. So in this case, so how are we going to tackle this problem? So we are doing some level of certain research to tackle this distribution shift in data, like which we call cross-domain federated learning. So here, what we do is that we split the parameter of this, the network into two, like the certain common parameters and some client-specific parameters. And these common parameters are, we can see some kind of like public key in encryption, and client-specific are called like a private key in the encryption. So that ensures the security or the privacy issue, the security in communicating in the network. And and then we learn we have our algorithm that basically helps us to align this the features from all these clients into a common subspace to basically address this challenge of heterogeneity in distribution of data. So I'm not going into the detail here, and so then we did some experiments, and also we did both experiments in terms of quantitatively and qualitative form. So here in the quantitative, so MIUU is like mean intersection of union. So higher is the better in this case. So here you can see that we compare our methods. So this is our method, the last column, and these are the different contemporary methods. So independent INDB means what if you were training your model independently. So in this case, for example, this Indo-UDA, like it has very small amount of training data. So the number is quite low. So, but when you go to our method and do in a federated manner, the performance has boosted from 52 to 62. So meaning like, even if you have a small amount of data and if you can collaborate securely without sharing the data, just parameters, so the performance can enhance. So basically from this result, it shows that our method is like, definitely better than this independent and other combined. This is like data lake and other contemporary federated learning method. So another aspect that I mentioned was like it is computationally expensive, right? So towards that, we are also developing novel algorithm to estimate the importance of neurons, because in deep network, all the neurons may not be important. So we have our own method to identify less important neuron and discarding them during the inference time and reduce this computational cost. I am going to show you here a demo that compares before and after application of our algorithm. So this is the inference time, and for the same image, the original before our algorithm, this is the time, inference time it requires. and the right-hand side shows the time that is required with our method. So basically, it reduces the inference time by a large margin. Next year, the use case that we are working on is retinal disease diagnosis. So optical coherence tomography or CT images are the scans of retinal layers, and they are used to diagnose different retinal conditions. So the task here is to, given this OCT images, to classify one of the 4 diseases categories. So one of them is, so we took this data set and then also applied the federated learning. In this case, so the dataset was there, so publicly available dataset was there, but we created an environment that where there is a simulated environment there where there is distribution shift in diseases. For instance, so these are the 4 clients, different clients, and you can see that in the NHS data distribution there are only 3 type of diseases, and the first 3. So then in UCL data distribution, so there is the second one is missing, and there is another in the another client, the third one is missing, and so and so. So here this is called like distribution shift in diseases. And to tackle such a scenario as well, we develop a federated learning mechanism that basically addresses these challenges. So not going into the details here. So these are the clients. For example, this can be NHS, and this can be a model trained in UCL or the other clients. And these clients models are shared to the server, and they are aggregated with their model parameters, as well as we impose a constraint that these model parameters the client model parameters do not shift that away from the mean parameters. So here is the results. So you can see here, like Fed average is the federated learning method, and federated data lake is when the data are combined in a lake, meaning like bringing all the data in a lake and training a model. So this is the federated one, learning mechanism. This is a federated data lake, and these are the performance due to standalone, means like what happens if they train themselves with their own data. So here you can see this number, accuracy higher is the better. So Fed average is as good as federated data lake. It means like combining the data in a same server and training it, right? So the performance gap is not statistically, it's not different. So they are the similar, but the federated learning, the advantage, this privacy advantage, or the federated learning algorithm brings is enormous compared to federated data lake. And if you see this number, I mean, if they were training themselves without sharing the model parameters, then the performance is quite low. It's in the range of 60%. And this is the last use case that we are also working on. So this is about how we can basically, be able to integrate multiple sources of information to train an AI model, but in a federated manner. So we can see it. So this is the X-ray image, and this is the clinical findings. And so the network will take both the information and process it and make a prediction. So this is something like we human beings. So basically we perceive information from different sensory organs and make a decision. Similarly, what if we can use these different heterogeneous sources of data in AI algorithm too? So, but then the problem with dealing with such data is that you might not be able to get all the information in every client. So there can be the heterogeneity in modality. So this is also another challenge in federated learning. So some clients, the institution, they can have both images or text, or I mean, we are just taking the example of image and text here for the experiment purpose, but definitely we can consider other modalities too. So then what happens if there is uneven distribution of these modalities, and how we can do federated learning in this scenario? So towards this, so we have proposed a a novel mechanism called augmentation by retrieval. And this is the work which is under review now. And the idea here is that, there can be certain small number of paired example like image and X-ray, and then their clinical findings. And that can be like, there are certain cases that these are available publicly. Then we come up with an idea of, a novel concept of finding the closest missing modalities and augmenting them before doing this federated learning thing to balance this out, the missing modalities. So the techniques, the method that we proposed also bring a lot of advantage in terms of performance. Like these are the number, like AUC, area under the curve. So higher is the better. And we compared with, different existing methods. And this proportion means like how many percentage of clients have like image, text, or both modalities. Like for example, this client has 40% image only, 0% text, and 60, percent both the modalities cases. And we also consider like heterogeneous and homogeneous condition. So in both the cases, our method has been quite useful to generalize better. And these are the also like we observed that, basically it is even useful when the data points for certain specific diseases are underrepresented, like means small in number. Right. So in the future, we are working on this following direction. So one of them is enhancing the security. So basically encrypting the models and parameters while sharing across the network. So because as I said, like these parameters are, although they are already encrypted or not interpretable, but still, we can uncover a certain level of information. And scalability. So we are also working on like how to manage larger and more diverse data set. And one more thing that we are working on is self-governing. So how to, basically in this, the existing method is like, so we know who are the clients, who are the institution they are going to collaborate, and what kind of data they have. So that's already known. But imagine like if you want to go to a very large number of scale of clients and allow like whichever clients wants to join and participate in the federated learning. So then there can be certain malicious attacks too. So and then there can be certain less important clients. So we are also working on like how to make this federated mechanism, which is self-governing, like identifying such malicious attacks, stopping them from sharing joining the network and learning process, and also identifying the less important clients to reduce this computational overhead cost. And we definitely would like to lift our methods for real world implementations. This is for like, which basically bridges the gap between research and clinical practice. So thank you so much for your attention. And if you have any questions, please feel free.
I have a question. Three questions. So I'm not sure if you can hear me. Can you hear me?
Yeah.
Yes, is deep learning the same as unsupervised learning? And with issues of large dimensionality in medical data, is deep learning also capable of doing dimensionality reduction? That's question one. Then for the second question, in creating federated data lakes, do you not still have some elements of data sharing in that? Also, is there a risk of interoperability of systems in creating federated data lakes? Would legacy systems be sufficient to create, that centralized server and database, or would you require new IT systems to be able to do that? Would systems be able to integrate or operate with each other seamlessly?
Okay, so your questions were, one was that is it about dimensionality reduction? Did you say like?
Yes, so it's deep learning. Would you say deep learning and unsupervised learning, are they the same thing?
So deep learning, so unsupervised learning technique is when we don't use any labels. For example, label in the sense like, for example, you are taking the X-ray scans and then you label it like whether there is some anomalies there or not, and if there are certain anomalies, then basically you can also categorize them into different level of different types of anomaly, right? Then using this data, not only in scan, you are using this label as well, to train the model, then that is supervised, okay? Unsupervised means like there is no label, just you take the scans and then you learn certain, the features. So that's unsupervised. So the deep learning and unsupervised is, so unsupervised and supervised are a type of learning mechanism like machine learning, and deep learning mechanism. And deep learning is one of the machine learning technique. So this is, deep learning can also be, unsupervised. We can train deep networks in an unsupervised way as well. So, and then about your dimensionality reduction, yes. So there are certain architecture called encoder decoder. So basically they are commonly used for dimensionality reduction. So what they do is that they take input image and then they project into low dimension space, and then they learn the parameters to reconstruct it back again. Okay. So then this projection, this small, basically you learn the parameter to project, the fit the data into low dimension. Like it can be 100 dimension, if you have image of 400, let's say that, 400 by 400, let's say, then still you can basically project into 100 dimension, 80 dimension, or 20 dimension. And, so dimensional reduction can be done with deep learning, and we can do it in an unsupervised way. So does that answer your first question?
Yeah,
And
yes.
okay, the second question is about for the federated learning. So we might need to upgrade the infrastructures. Do we need to do that or not? Is that your question? Just want to
Yeah,
confirm.
that was like the third question.
All
The
right.
second
So
question was about data sharing in federated data lakes.
okay, in the federated data lakes, we share the data, right? But I'm not working on the direction because that is something like shipping the data from one center to another center, and it brings the privacy issue, like every privacy issue that exists there. Okay. So what I'm interested in is how I can train a model, learn the model, or share the experience without sharing the raw data. Okay. So here we don't share any data. We just share the model parameters. The parameters are, some weights in the form of matrix. So these are the numbers only, right? So unlike X-ray, let's say if I take an X-ray, so there will be like X-ray image, the scans and everything anatomical and all this thing information would be there, right? But here in this case, just weights, the numbers, the matrix numbers will be there. So that's basically not, they are uninterpretable, right? So there is no such issue. But as I said, like still from those numbers, we can uncover certain level of information, right? So that's why they are still prone to certain level of security issue. Right. So about upgrade, so data lake can, if you want to bring all the data and train a model, then you might need to expand your infrastructure. But here in this federated learning, the idea here is that you can have like, certain your own client or the existing infrastructure, right? Then just one thing that might need to upgrade is that server. In the server also, there is no such computation. It's just about like, getting the model from different clients and averaging it. So it's not that computational expensive too. So in fact, federated learning helps us to optimally utilize the resources that we have. You have, or another institution have, they have their own infrastructure, right? So basically it actually optimally utilize such resources because the data is fragmented and even computational is shared between different clients, right? So it does other way around, actually.
Okay.
Thank you.
Thank you very much. Unfortunately, we're out of time. We're a little bit behind time. So thank you so much, Binod, for your very interesting presentation and sharing all your thoughts. It's all been recorded. as you are aware. So for those of you who would like to listen to it later, as well as those online, you can. We will make sure it is distributed later on. We're going to have a short break now, a short coffee break, and then we'll take you from one data lake